welcome to my video. So in this video, I'll try to explain in the most simplest way what's happening inside a proton. So this is a dramatic view of a proton, and if this is a proton, then these are quarks. Yes. So a proton consists of quarks, and these quarks always come in triplets. That is, you cannot ever separate them. They are never isolated. And you might think what these spring-like substances are. Well, those are called as gluons. And what are gluons? Gluons basically binds the three quarks. And gluon is also a force carrier. What is a force carrier? Well, the best way to explain what a force carrier is by a thought experiment. Consider there is a very big field, okay, maybe a basketball field. You are there and your friend is there standing opposite you. Your friend thinks of throwing a ball at you so that you will start playing, okay. So your friend throws a ball, you catches the ball. After some time, the speed of the ball increases, or in other words, your friend starts throwing it at a much faster rate. So what will happen? You might go back or you might come friend, right, to catch the ball. Also, while the ball is being thrown, it's indirectly connecting you and your friend. Imagine the ball to be very fast. Then, you and your friend seem to be connected, but are not quite connected, right? So what does the ball do? The ball actually gives or actually shows the existence of you and your friend. That is, if the ball is not there to mediate in between you and your friend, and considering that you and your friend has no the basic five senses, then what is a proof that you actually exist in the field? There is no proof. So the ball kind of shows or proves your and your friend's existence. And it's because of this ball, momentum caused by this ball, that sometimes you might go back or come friend, right? So that is exactly what a force carrier does. It carries force. And what happens when it carries force? It causes changes in the two particles. Here the force carrier is a ball, the quantum field is the big basketball field, and the particle is you and your friend. And what is a force? That is something that comes into existence when the force carrier is being exchanged between you and your friend. So here the gluon acts as a force carrier. Force carrier of which force? Of the strong force. And believe me, this strong force is stronger than a Hulk. Every force, four fundamental forces in nature have force carrier. For example, for gravity or gravitational force, we have gravitons. It's a theoretical particle because it has never been actually found, but hopefully it will be found one day. In electromagnetism, we have photons. Same way, in strong force, we have gluons. So that is the function of gluon inside the proton. So because of the gluon, it's impossible to ever separate the three quarks inside the proton. No matter how much ever energy you give, you won't be ever able to isolate the quarks. So quarks are always found in triplets. But as you can see, I have written some random up, top, down, bottom, strange and sharp. And I have only specified three quarks. These are actually different types of quarks, okay? But inside the proton, you only find up quark and the down quark. What happens to top, bottom, strange and sharp? Well, they are massive. And what happens when a subatomic particle is very massive? They decay into less massive particles. That is what's happening. Sharp, strange, bottom and top will decompose or decay to up and down, and therefore you always only find up and down quarks inside a proton as well as a but the other kinds of quarks are found during cosmic rays and also in particle accelerators. And what is the property that differentiates an up quark and a down quark? That is very interesting. We call it color charges. Well, colored charges do not have any color. It is just a random name given. So you know, for electron, for an electron you have charge 1.67 into 10 raised to minus 19, right? Similarly, for a quark also they have specific charges, and it is because of those specific charges that a proton is actually positive. We will see that. So inside a proton we have two up quarks, it's already written over there, and one down quark. Okay, so two up and one down. What are their color charges? It's found out that up quark have plus 2 by 3 plus 1 by 3 actually. 1 by 3 plus 1 by 3 2 by 3 itself minus 1 by 3, then only it's conserved, right? So 2 by 3, 2 by 3, and the charge of a down quark is minus 1 by 3. So what do you get at total? Plus 1. That's how proton has its charge. And what makes a neutron differ from a proton? It's a combination of these quarks. That is 2 down and 1 up. So you can guess it right now. Minus 1 by 3 minus 1 by 3 plus 2 by 3 equal to 0 charge, thus making it neutral. If you know about quantization of charges, you might have already observed this doesn't actually follow the electronic quantization of charge. That is Q equal to Ne. What is Q equal to Ne? You consider there is a charged body, then the total number of charges in electronic charge to be specified inside the body will always be an integer multiple of the charge of a single electron. Well, that quantization of electronic charge does not take place here, because you can see here it will always be 1 electron, 2 electron, 3 electron, 4 electron, like that. You will never have 2 by 3 electrons in a charged conductor, right? But here for the quark you can see the charges are 2 by 3 minus 1 by 3, and there are a lot more. So that is the difference between this charge and the electronic charge. So please don't get confused. Another interesting thing is it follows Pauli's exclusion principle. And what does Pauli's exclusion principle actually say? Pauli's exclusion principle says that two subatomic particles cannot stay in the same quantum state. So you might think, well, if I go to the market, I am always at the market. Or if there is nobody else to be in the same position of where I stand, right? If I am at point B, I am the only person who is at point B. Isn't that true for subatomic particles? Well, no. For particles like photons, which is particle found in light, they do not obey Pauli's exclusion principle. But quarks thankfully obeys Pauli's exclusion principle, thus making things more easier. Then I explained about the color charge and electric charge analogy. That is, color charge, one more way of understanding is an electric charge produces field lines like this, right? They produces field lines like this. And if another charge is kept over there, they will feel attraction, right? If it is negative attraction, positive repulsion. Same way for color charges do produce field lines, but they are kind of different because we have the much effective gluons in between. So it's kind of like this. You can see the break happening over here. This is actually caused by gluons. Mathematically, it's even more difficult to explain. So it kind of starts looks like this. Well, gluons can also be represented by Feynman's diagrams, which will explain things more easily, but then they are kind of out of the scope, so we'll stick on to these basics. So that's how we have that's how color charge and electric charge have an analogy comparison. Just like all forces, just like all force carriers, which is there in each kind of forces. In strong force, as I've already explained, we have gluons. Okay, we have gluons. So you might think if quarks can never be isolated, how have we ever observed them? Well, just like we saw an electron or a proton, we have never ever observed quark. We have only observed its presence, the changes it brings when it is there. Okay, we cannot ever see it because one, it's very small, second, it cannot be isolated. So through experiments, its presence is observed. That's how quarks is found out. So that's not all about quarks, but these are some very basics about quarks. One thing that mesmerized me is, see how strange these subatomic particles behave. But when we come into the macro world, they are not so strange, right? In fact, all these should actually be named strange. I hope you enjoyed my video. I hope you understood what a quark is and what makes a proton different from neutron. It's just the quarks that is present inside a proton and a neutron that changes its charge, nothing else. And remember one thing, as I've already said, when I said color charges, they are not green or blue or red. They are just ways of representing it. It's just a very unique name given to the charge possessed by the quark. I hope you enjoyed. Thank you. Bye-bye.